Welcome back from that short break. Now it's time to have a look at how electromagnetic waves travel through or not through a medium. Let's jump back onto our concept map to remind ourselves of what we've been talking about. We've already related the behavior of waves to electromagnetic phenomenon, and we've looked at the behavior of particles and tried our best to relate it to electromagnetic phenomenon. We related the uniqueness of the speed of electromagnetic radiation. Now it's time to understand how it propagates. Have you ever seen light being made? Have you ever seen any kind of electromagnetic radiation being made? The answer is no, not at least with your naked eye. So how does it form and how does it propagate? Let's have a look. For us to understand how it propagates, we first need to know what propagate means. Propagation is the spreading out or the dispersal of something. Now, if you've ever turned on a light in a room next to your room and left your room in darkness, you've been able to see how light propagates out of the lit room into the adjacent room. The next key word we need to familiarize ourselves with is that of a field. Now, in physics, a field is not something that we play sport on. It is in fact a region in space where objects experience forces. You may have examined or heard about fields before. Can you think of any examples of fields that we've worked with already, or perhaps fields that you've heard of mentioned? We often in movies talk about an electric field. Do you think that there's an electric field involved in electromagnetic radiation? I certainly hope so. Let's have a look at fields in a little bit more detail. We said that a field was a region in space where an object experienced a force. We get different types of fields, and the first one we're going to be looking at is an electric field. Electric fields are usually given the symbol E, and they are simply a region in space where a charged object will experience a force. All right? A region where charged objects enter the space and then experience a force. Have you ever experienced electric fields in your own life? You probably have without ever realizing it. Have you ever had a blanket and run it over your head and then had all your hairs stand up? Maybe you've seen in movies or on TV when people touch the dome of a Van de Graaff generator, their hair stands up. Or someone who's been electrocuted in a cartoon has all of their hair standing on end. The reason that the hair stands on end is because electric fields are generated around each individual hair that repel one another, causing them to stand up and as far away from each other as possible. Another type of common field that we need to examine is magnetic fields. Now, you experience them in your everyday life as well, but perhaps you don't know all that you should know about them. Let's have a look. So magnetic fields are, again, just a type of field, and they are given the symbol B. In fact, sometimes they're affectionately referred to as B fields. A magnetic field is simply, again, a field, which is a region in space, but a magnetic field specifically is the type of field that forms around magnetic objects. When another magnet or object made of a material that is considered magnetic enters this space, this field, it then experiences a force. Now, the magnetic fields that you and I experience in our everyday lives are not quite like the ones that we're going to be looking at in terms of electromagnetic radiation. They tend to be much bigger and quite a bit stronger. And usually when you and I think of magnetic fields, we think of simple fridge magnets, or maybe even electromagnets like you see used to pick up scrap cars in a junkyard. But the question is, how do electric fields and magnetic fields relate to one another, and how do they work together to allow electromagnetic radiation to propagate from one place to another? Well, let's have a look. I often encourage my learners when working with complex terms like electromagnetic to break the words up into components. Sorry, the slide's gone the wrong way. Just get the pen active. To break the word into components. Two obvious components here are electro and magnetic. Now, the electro part of the phrase refers specifically to the electric component of the wave. All right? And this is related to a changing electric field, i.e., when we talk about electromagnetic waves, we are literally in part talking about an electric field that is itself changing. The word magnetic, again, refers to the magnetic component of the wave. This is related, again, to a changing magnetic field. Now, this all might seem a little bit disconnected right now, i.e., how does an electric charge or the moving of an electric charge to make a field cause a magnetic field to occur? What kind of relationship exists between the two? How can we use them or relate them so that we can understand electromagnetic, the combination of the two, and how it propagates? When posed with such a complex word like electromagnetic, I often encourage my learners to break the word up to better understand each component one at a time. In the phrase electromagnetic waves, we have electro, which refers to the electric component of the wave, and it is related to a changing electric field, i.e., electromagnetic waves are in part made up by a changing electric field. The second word, magnetic, again in the same vein, refers to the magnetic component of the wave. And again, it relates how a part of the wave, a component of the wave, is made up of a changing magnetic field. But where do these electromagnetic waves originate from? Well, they originate from an accelerating charge. Now, in our investigation of the realms of physics and chemistry, we've only seen two types of charged particles: protons, which have a positive charge, and electrons, which have a negative charge. Now, you can imagine that getting to a proton trapped inside a nucleus can be quite difficult. So when we look at the propagation of electromagnetic radiation, we focus quite a lot on the role played by the electron. The electron, a negative charge that accelerates, is what causes or generates most of the electromagnetic radiation we have discussed or had a look at in these last few lessons. So let's have a look. When electrons are accelerated, they generate a moving or changing electric field. When this electric field is generated and moves, it is able to cause a magnetic field to be generated as well. i.e., if you ever move a charged object, you immediately induce a magnetic field at 90 degrees to the electric field associated with that charged object. And to help us visualize how these two electromagnetic waves appear, you can imagine the changes in each field as transverse waves. Now, this is all well and good, but how is the nature of the fields being generated by moving charges and them generating magnetic fields in turn able to propagate an electromagnetic wave through space and potentially time? Let's have a look. I've got an animation that should prove quite helpful. So in this animation, you can see that we have an electric field marked in blue and given the symbol E, and a magnetic field in red marked with the symbol B. And as you can see, as each field is generated, a complementary field at 90 degrees is also generated of the opposite type. So to put this into words, we say that each new electric wave generates a magnetic wave that then repropagates an electric field. The electric and magnetic fields induce one another, i.e., they cause one another to occur. And it is this repeating pattern that we consider to be electromagnetic radiation. This induction is self-propagating, which means that electromagnetic radiation does not require a constant source of energy. And this is also why electromagnetic radiation can travel without a medium, because an electric field and a magnetic field do not require a medium. All right, so now we've come to the end of our introduction to electromagnetic radiation and the electromagnetic spectrum. I hope you've enjoyed it and found it interesting, and I'll see you next time.